Assalamualaikum warahmatullah. Students in section 5 and section 6, heat transfer SKMM3443. This module, which I have to break up into a few parts, will cover external force convection. What will be covered will be general external flows, and then parallel flow over flat plates, which involve laminar as well as turbulent flow conditions, and flow over solid bodies like a cylinder and a sphere. Earlier, we learned that convection can be either forced or free. Force being requiring external force like a fan or a pump to induce the fluid flow over the solid wall. For free natural convection, we do not need external forces. Right. For forced convection, there is external force convection as well as internal force convection. For free, we have only external free convection. Why do you think there is no internal free convection? For convection, we have to know the Newton's law of cooling. I hope by now you could say it from memory. Go back to 6162. Here, the very simplest example, we have the solid wall at temperature Ts, and we are interested to know the heat flux or heat transfer from or to the solid wall. So for an external flow, the boundary layer can develop freely without constraints of adjacent surfaces. There will always exist outside the boundary layer where the velocity or temperature gradients are negligible and can be neglected. Some of the examples of flow over solid bodies are these over a flat plate, which we encounter often. Flow over a cylinder, a circular cylinder here. It could be any other geometrical cylinder and any other arbitrary shaped body. But in this course, we shall focus only on the low velocity force convection with no phase change. Low velocity means nothing above 3-digit meter per second, or no phase change like evaporation or condensation, because such analysis is very complex. The relative motion between the fluid and the surface is maintained by the external means. And drag force is due to the pressure and wall shear stress forces acting on the surface in the flow direction, that is drag. And we have lift that is perpendicular to the direction of the flow. The drag force depends on the density of the fluid, the upstream velocity, size, shape, and orientation of the body in the fluid. Now, the main concern here in our convective heat transfer analysis is the correct H, so that we will get the correct heat transfer. Okay. The Nusselt number introduced earlier is HLC over K, and the subscript X here refers to the location along the direction of the flow. Now, the average means the value is taken from the leading edge over the whole plate up to the location where you want to analyze the heat transfer. There are two approaches to obtaining H actually. One is exact solution, is the theoretical approach, where the Nusselt number is obtained by solving the boundary layer equations, the mass, momentum, energy, for specific surface geometry. For now, the only exact solution to obtaining H is a flow over a flat plate, isothermal flat plate. The second approach to get H is the experimental or empirical approach, where the Nusselt number is obtained through a series of laboratory experiments, heat transfer under controlled conditions to obtain dimensionless correlation. So these experiments that have been done by researchers may involve different fluid, different lab conditions, etc. And they may come up with similar form of correlation, or may be different. There are actually many correlation for H. In this class, we are going only to see a few. We will look at the empirical approach first. Yeah. So for a variety of test conditions, to obtain different values of Nusselt number for different velocity, upstream velocity, different plate length, and different fluids, because different fluids at different temperature have different Prandtl number, like air, water, engine oil, will give results such as shown on a log-log scale. Yeah. Now, in general, the empirical correlations obtained by researchers are of this form in 7.5, where the average Nusselt number, you see the subscript L means it is flowing over a flat plate. Yes. There is a C, constant, and index M and N appearing there. The values of C, M, and N are between 0 and 1, and often independent of the nature of the fluid. They depend on the nature of the surface geometry, whether it's smooth or rough, and the type of flow, whether it's laminar or turbulent. The variation in fluid properties within the boundary layer affects the heat transfer rate, and this can be accounted for by using the two approaches actually, to get the properties. The first approach is the most common one, and I recommend you to use that. That is obtaining the thermophysical properties at the film temperature. What is the film temperature? Film temperature is when you are given the surface temperature and the pre-stream temperature, and you take the average of that, and you obtain your thermophysical properties at that film temperature. Don't forget your assumption that these thermophysical properties obtained at the film temperature are assumed constant throughout the plate where you analyze your heat transfer. Okay. The second approach, which I do not recommend because it's quite involved, yeah, you have to evaluate the properties at the approaching velocity of the fluid, and then multiply with an additional parameter to account for the property variations. Yeah, the parameter is of the form Prandtl number, or at the temperature of the free stream divided by the Prandtl number at the temperature of the surface of the solid to some power. Yeah. For this class, I think we will only look at the approach 1 to obtain the thermophysical properties. Yes. For the theoretical method, there is only one solution I mentioned earlier, that is for flow over a flat plate, and it's laminar, and the plate has a constant temperature, isothermal. Okay, so in the boundary layer, conservation of mass, momentum, and energy in two-dimensional, which is presented in chapter 6 of the Cheng-El textbook. Yeah, so we have these three equations. By the way, what happened to the velocity in the y and z directions? This one. You see, note that this is only the axial velocity, yes, change with the x direction and the y direction. Okay, there is no z direction because we are analyzing only two-dimensional. But what happened to the velocity in the y direction, the y momentum? Think about that. Yeah? For constant properties, conditions in the boundary layer are independent of temperature. Again, at what temperature should you obtain the thermophysical properties? At the film temperature. Now, results from the Blasius solution. Yes, we have this. This is obtained from Incropera, because I've used my notes based on the Incropera reference book. You're using Cheng-El, and this is from Cheng-El. Okay, it's a difference here, but it's up to you to use which one. Okay, and the local friction coefficient is obtained from 654. Subsequently, the ratio of the velocity boundary layer to the thermal boundary layer is found to be such. Okay, so notice there is a the velocity boundary layer, or the hydrodynamic boundary layer, or just plain boundary layer, and here we have the thickness of the thermal boundary layer. For laminar parallel flow over an isothermal flat plate, the exact solution obtained is this. Yes, for Prandtl number greater or equal to 0.6. That means if the Prandtl number is less than this, you cannot use this equation. And the second condition is the Reynolds number is less than 5 times 10 to the power 5. That is for lamina. Remember we said here, this is for flat plate, lamina, isothermal condition. If it's not flat, if it's not lamina, if it's not isothermal, then you cannot use this Nusselt number. Okay, so what happens to H at the leading edge? If you notice here, at the leading edge, X would be 0. So H would be very, very high. Maximum, as we've seen in chapter 6. But when we are doing heat transfer analysis, we're interested to know the heat transfer over the whole plate, right? Most of the time. Okay, so for most of the time, to get that, you need to know the average H, and to get the average H, you need to know the average Nusselt number from this equation, right? That equation, and the condition is Prandtl number must be greater than 0.6. So you note that the average convective coefficient is twice the local convective coefficient compared to this. See, 0.664 is twice the 0.332. Okay, for the turbulent case, the Nusselt number has been obtained through correlations. We shall look into that later. So for now, the exact solution is this, which come to 719 or 721, whichever that is. This is again for flow over a flat plate, lamina, isothermal condition. And the thermophysical properties are all obtained at the film temperature. Yes. For the correlation, we shall look at several correlation, I believe, that is of this form. That is all for this part of the module.